Today, in just a minute, I'm going to be welcoming Dr. Julia Kelson. And first, I'm going to tell you a little bit about her talk as a teaser. So she says, we are currently witnessing one of the most dramatic climate change events in the Earth's history. This begs the following question. How has Earth's climate changed throughout geologic time? So today you're going to get a glimpse on what that means, and you're going to hear from Julia Kelson. Welcome, Julia. Hi, how are you today?
Going well. How are you?
I'm good. Well, thank you so much for being here. So Dr. Julia Kelson's research seeks to reconstruct climate during the so-called hothouse periods of Earth's history, which corresponds to high concentrations of carbon dioxide in the atmosphere. She uses the stable isotope geochemistry of ancient soils to understand the evolution of temperature and aridity in terrestrial environments. She's a California native with a passion for granite landscapes. She has a BA in Earth Sciences from Dartmouth and a PhD in Earth and Space Sciences from the University of Washington, Seattle. And she is currently a National Science Foundation Earth Science postdoctoral fellow at the University of Michigan, Ann Arbor. And we are so excited to welcome Dr. Julia Kelson. I'll let you take it away.
Hello. So I'm Julia Kelson. I'm a postdoctoral researcher at the University of Michigan. And essentially what that means is that I get to do research on questions that I find interesting full time. So I get to think about interesting questions in geology and then plan how to answer those questions. And so what I'm working on right now and what's motivated a lot of my research is understanding climate change in geologic time. And I do that by using soil geochemistry. And more specifically in today's talk, I'm going to tell you about the project that I'm working on this very second that's trying to identify aridity and how aridity has changed through geologic time, specifically using evaporation and the evaporation that we can detect with stable isotopes of soil carbonates. And hopefully that explanation will make a little bit more sense by the end of this talk. So again, just the kind of big picture motivation for my research is that the Earth is warming right now. And this here I'm showing you a classic climate science figure that was first published in 1998. And this is called the hockey stick figure because it looks like a hockey stick. So starting in 1900 with the time of the Industrial Revolution, when humans started emitting greenhouse gases, we can actually measure that there's been an increase in average surface temperature correlated with the increase in greenhouse gases. And so scientists actually predicted this, and we've been able to measure it, and we know that it's happening. And we've probably learned about this in our sciences classes, but as a brief reminder, we know that greenhouse gases like carbon dioxide act to warm the Earth's surface. And so as most of the heat on the Earth's surface comes from the sun, and that comes in and hits our Earth as incoming solar radiation. And then when it's absorbed by the Earth, it changes wavelength and tries to escape as thermal radiation of a different wavelength. But turns out that carbon dioxide and other so-called greenhouse gases are really effective at trapping that outgoing thermal radiation. So as we increase the concentration of greenhouse gases in the atmosphere, we increasingly heat the surface of the Earth. So we're confident that this process is affecting our current Earth climate. What we're less confident about is exactly what magnitude temperature change we might expect to witness as a result of those increasing concentrations of greenhouse gases in the atmosphere. And in addition to the temperature response, there's kind of a whole series of other climate responses to this, into what we call greenhouse gas forcing, or the increase in temperature. And so we've already, this is probably intuitive for those of you in California, especially given this current wildfire season. We know that there are going to be other climate responses to this increase in temperature. And one hypothesis perhaps is that wetter zones will get wetter and drier zones will get drier. And so we might observe increases in regional aridity that might result in something like more intense and severe droughts in the future. But so my approach to trying to answer these questions is actually by looking at the past. And so I'll explain to you why I think the past is at least one way or one key to understanding the future warming. So to sum this up, the geologic record offers a valuable perspective of climate change in hothouse worlds. I'm interested in the early Eocene because this is one of the time periods that we know is extremely warm, and there's a lot of carbon dioxide in the atmosphere. So we think that these time periods are good analogs for future warming. And soil carbonates are one of the few tools that we have to investigate those ancient climates, especially on land. So I showed you that we have a pretty good record of how temperature has changed through the deep ocean, but on land, the record can be more difficult to find. But soil carbonates are one of the few tools that we have to reconstruct ancient climate in deep time. And what I'm working on right now, and hopefully what you feel like you have an understanding of, is developing stable isotope tools we need to be able to interpret those archives that exist. Those rocks are out there and they know what the climate was like. It's just a matter of us figuring out how we can read the climate record from those rocks. And thank you all for your attention. Here are these are Eocene alligators. This is a joke that a friend of mine developed, but all of these alligators are laughing at this. This alligator was at the North Pole in the early Eocene, and he went on a trip to the North Pole and he brought his coat, and all of these alligators are laughing at him because he didn't know that it was already warm at the North Pole during the Eocene. All right, so
fascinating to kind of take a trip back through history and then to modern times and kind of learn about what you might be studying in the future. And so how did you initially know that you should start by analyzing today's soil in order to look at the soil of the past?
Well, to be totally frank, we definitely do them both at the same time. So we don't always start with the modern and then work in the past. Often we measure soils in the past and realize that we aren't fully able to interpret their isotopic composition. And so then we turn back to modern and measure modern soils to see if we can use a place that we understand its climate, and we know the conditions under which it's forming. Okay, what does the isotope look like there? And then we go back to the past. And so they definitely inform one another. It's a fluid process where we go back and forth between understanding the modern and the past.
I know that your field of study is quite specific. How did you refine it to become something that you're so passionate about that's so specific?
So I didn't exactly start knowing that I wanted to study geology, but in a couple of years, I realized that I was really passionate about studying the Earth, both because of its and human effects on the climate, and because, the Earth, the landscape that we live in affects pretty much every bit of our daily life in ways that we don't fully appreciate. So I think that motivated me originally to study earth science. And then when I started my doctoral research, my PhD at the University of Washington, I kind of zoomed in on this really narrow part of geology, initially interested in climate science. And then part of what I work on is driven by what are the big outstanding questions in geology, and how can answering those questions help humanity.
I'm wondering if you can share a little bit about your day-to-day research. I know that you got to spend some time in the field, and we've heard from some scientists who spend a lot of time in the lab. It sounds like you kind of have to balance both.
Mm-hmm.
What does your work look like?
Right. Yeah, so I always joke that, another reason that I wanted to become a geologist was because I love the outdoors and I love being outside and I love the field work. In reality, I probably spend 3 weeks out of the year in the field at most, and I spend most of my time in the lab doing the analysis, and also even more of my time on the computer writing and reading, and both finding funding for this research, being a scholar, so reading papers, understanding those papers, writing my own papers for publication.
So we're going to wrap up soon, but I wanted to know, to maybe kind of leave the audience with something that they can do. I noticed that some of your most recent field research was in fairly close together areas in California, Livermore, Sierraville. They're not really that far away. Is this kind of research something someone could go do maybe in their backyard and then drive a couple hours and look at some other soil? They wanted to just kind of get a beginner's experience?
Yeah, absolutely. Especially in California, it's kind of an interesting place to study how soils develop in relation to climate because there are such different climate states within driving distance. So even the San Francisco Bay Area has kind of a microclimate where San Francisco itself is quite cold and foggy, and then you go over the Bay Area hills and you're in the Central Valley and it's hot in the summer and drier. But absolutely, you could go dig a soil pit or even just look at road cuts of soils and probably observe for yourself that the soils that form in those different climate states are quite different than they are. Yeah.
Mm-hmm. Great. Well, if you're watching, go dig a soil pit. If you're a little kid, ask your parents first.
Awesome. Thank you.
Thank you.